Okay, we retain an interesting integral. We've got the integral from 0 to 1, natural log x over 1 plus x dx. Okay, this one came out of the comments. I did this exact same problem recently, but in the comments there was a suggestion that we could do this straight away using geometric series. Just noticing that if there's a 1 right there, I can actually write this as 1 over 1 minus x, because our geometric series formula is just 1 over 1 minus x equals the sum from 0 to infinity of just x to the n. And so for what we have here, I just need to change it just a little bit to make it fit this form. So we can write it like this. So our input's minus x into this. And then for our sum, this is going to become minus x to the n. For the convergence on this, we just need absolute value minus x to be less than 0. The minus sign doesn't matter inside the absolute value. And we just notice our bounds are from 0 to 1, so this is going to be fine. And so what we can do is we can take this right here and we can throw it back into the integral. So now when I do this, what I'm going to do, let's leave the natural log x in front. And then for the sum part of this, for minus x to the n, I can write this as minus 1 to the n times x to the n. So we'll just break it up like that. Then let's rearrange it, just multiplying in the ln x inside the sum. And then from here, let's just swap the order of integration with the sum. We're fine doing it because we determined absolute convergence over here. So let's just go ahead and do the swap. Now minus 1 to the n, that's just a constant with respect to x, so I can bring this up front of the integral. And then with what we have left, given my choice, I'd probably just do a u substitution, because then what would happen is we would get it in the form of the gamma function, or I guess we'd have it in the form of a Laplace transform. The only thing is that's probably too similar to what we did in the last video, and I'm kind of looking for a different method. So in order to do that, let's do integration by parts on this. Okay, so for integration by parts, let's use the DI method over here to the right, where we'll differentiate ln x, we'll integrate x to the n. When we do that, differentiating this, we just get 1 over x. Integrating here, we're going to get x to the n plus 1 over n plus 1. I could keep going, but I think I'm just going to stop right here. We'll have part of our solution on the diagonal here. And I think I'll evaluate this separately before I plug it back into the integral. So for this part, we're going to have ln x n plus 1 over n plus 1. We need to evaluate this from 0 to 1. And then here for this integral, minus, but then if we kind of combine these, we're multiply these together, this is going to be like an x to the 1. So then we divide that into there, we're going to subtract off this one, and what we have is going to be x to the n over n plus 1. Now evaluating this first part, when you plug 1 in here, this piece is just a 1. ln 1 is just 0, so the first piece is 0. You plug 0 in, you're going to have an indeterminate form here, because the natural log of 0 is going to minus infinity. So you could use L'Hopital's rule here to evaluate this, but when you do that, you're just going to get the same solution, just a 0. And so this goes away, and then let's go ahead with this integral here. So when we do this, it's just going to be power rule. We get x to the n plus 1, and n plus 1 comes out times this is going to be n plus 1 squared, and we just need to evaluate from 0 to 1. Well, when you plug in 0, you get nothing, so we just plug in 1, and we get minus 1 over n plus 1 all squared. So let's take this and plug it back into our sum up here. So when we do that, we have this minus 1 to the n that we've already pulled outside of the integral. And then here we're going to have all this stuff, minus 1 over n plus 1 squared. Well, I can take this minus 1 right here and multiply it by this minus 1, and then with exponent properties it becomes minus 1 to the n plus 1. And then on this, what I can do is an index change, just subtracting 1 from n here, subtract 1 here, and we just need to add 1 here. So when we do that, let's see what it looks like all cleaned up. But then what we have right here is really close to the eta function at 2. Let's just look at that definition really quick. So if you plug a 2 into this formula here for eta of 2, the only difference is this plus 1 here on the minus 1. So all I need to do to make this look like eta of 2 is basically multiply in a minus 1 in order to get that, but I don't want to change it, so let's multiply by a minus sign in front. But now eta of 2 has a well-known value of just pi squared over 12. So putting this together with the minus sign on it, we get our final solution of just minus pi squared over 12. Okay, so there you go. Good suggestion from the comments. Really like that one. And this was actually very similar when I did the other problem. I don't remember what I did, if it was there were so many that were similar to this, but the same kind of thing came up. And so I think I did alternative methods on that other one too. I think I came up in the one from the UK integration bee where there was e to the x there. I don't know, the integrals are kind of all running together and I'm getting confused, but I know we did something like this before. Anyway, that's it for today. Thanks everyone for watching. Have a good day.